people are absent, I'll try and make sure they go up online. You may have to ask me where they are, and you're always welcome to ask me for the class notes if you want. So, yes, last week we looked at this, I'm just going to draw a picture, idea of linear approximation where you have some function and you kind of linearly extend it and you get an approximation using the derivative of that. And then we looked at these hyperbolic functions. And we saw how it's very practical if you're in the bubble business, and how I thought I could see it from where I stood. How like domes, I mean, it's a physics question, why is it? But to get the best, force ratio, get a nice strong dome, you actually want it to be in the shape of a hyperbolic cosine. So that was last week. These are kind of peripheral. In fact, a lot of what we do in this class seems to me peripheral. They're important things in math, but you guys, I don't sense too many math majors. So maybe if you're like going into applied math, this is a good starting point, knowing about linear approximation. If you're going to be doing a lot of approximating with computers. Well, these are a little esoteric, and again, you might run into them in architecture. You will run into them in math a lot, but again, as I said, my sense is most of your needs were more practical. Saying all that, the next section, I guess I'm just going to erase this. The next section, 411, maximums and minimums. Minimums are really these are close to the heart of this course. We learned how to do derivatives. That's this semester. That's really the key ingredient. But now there are things we can do with derivatives, and this is really an important one. You can read the section on the book; they'll give you more detail. But when you're dealing with, take your pick: economics, physics. You're doing a study, some sociological study, chemistry. All these things. Something's going on, and you want to know, like some maximum or some minimum. How hot is this chemical reaction going to get before it cools down? What's the maximum load that this structure can take? So this is a very important issue, and the main thing you you're going to know right away, and you're going to go, that's easy. And then there's some peripheral issues. So, that being the case, let's just take a look at some very standard kind of graph here. Y equals x squared. And this is a continuous curve, it's a polynomial. And it's differentiable everywhere. And so if I pick a point over here to the left of the origin, this again, the opportunity to use a different color. We can see that over here the slope is negative, and over here the slope is going up, it's positive. And as we get closer and closer to the origin, these slopes are getting, here they're getting less and less and less, and then they start increasing. So it shouldn't come as a surprise that when we get down here to the origin, to the minimum of this function, that the derivative is 0 is 0. Now this just happens to be a minimum, but same kind of situation would apply if you were, well, certainly if you're looking at an upside down parabola. You'd expect that the maximum, again, you're going to have a tangent which is horizontal, and again, you know, whatever that point is, the derivative will be 0. There's a proof of this in the book. It's kind of obscure, and it's for people who are interested in going on and learning about analysis. The basic idea is if you have a point and the derivative is not 0, right? Well, if you're dealing with a maximum here, if the derivative is not 0, the function is going to get greater. If you think about the linear approximation, you know, you're adding something. So if you have a positive slope here that's not 0, you're not at the maximum. So that's the basic idea behind the proof. I'm not doing anything formal here because again I don't see that as important. Right. So let's just do a simple example here. So I have some function 3 minus x squared, and I'd like to know if it has a maximum or a minimum. Figure out later. So the derivative, of course, is negative 2x. And we want to know where that's 0. And of course, it's 0 at x equals 0. Well, if we were to graph this, the apex would be up here at 3. At 0, we have this horizontal tangent. And if I plug 0 into my function, I get f of 0 equals 3, which is exactly, that's where my maximum is. That's about as easy as this kind of problem gets. I remember taught, high school algebra and pre-calc, and we're often like talking about, well, where's the maximum in the apex of this parabola? And we go through all sorts of contortions to find it. And we like to find the axis of symmetry and where that, what point on that axis is the function, and then figure it out from that. And here we have just a little calculus, which we can't tell those students. Here their head would explode, and it's very easy. All right, so that being the case, this is just kind of the simple version. There are a bunch of nitty details you have to deal with. All right, so let's take a look at some function that is not so nice. It's kind of going to go like this. Here, here, here. Okay. And just take my word, this is some polynomial function. It's continuous. And it appears that the derivative becomes 0 in a number of places. So over here, 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 and here. So the first thing to realize is that these places where f of x is, f prime of x is 0, they may be a maximum, but they're a local maximum or a local minimum, right? Clearly, this point is not as high as this point, but they both have this feature. So by itself, if you have a derivative 0, it doesn't tell you necessarily the absolute maximum of a function. We have to look a little further. Well, here it might be good to be a little more formal. So we're going to define a local maximum definition. Local maximum so f of x has a local maximum at C on some interval between A and B. If for all x in A comma B, f of c is greater than or equal to f of x. Okay, that's a very formal kind of math statement. Let's just deconstruct this. We have some function, and we're defining how we know it has a maximum, a local maximum. So there has to be some interval. Oh, in this case, we'll just say this is A and B. It has a local maximum if every value, every x in that interval is such that f of c is greater than or equal to x. It's pretty logical. Of course, then one can immediately define a local minimum the same way. Blah blah has a local minimum on some interval if for all a and b, f of c is less than or equal to f of x. So here we have a local minimum on this interval. Our value at c is always less. Okay, well, now we know what a local minimum is. I'm not going to leave that definition up. It takes too much space, but it's useful to know. So we have local max and min. And now we're going to look at what an absolute. The right hand can't spell either. Absolute max and min is. So like I said, there's a few little details here we have to straighten out. So let's say we have some function defined. It's defined on an interval a to d, where a is over here and d is over here, and it kind of looks like this. So we have a, f of a, we'll call this b, f of b, c, f of c, and d. Okay, so let's think about what we have here. By our by our previous definition, we've got a local minimum here at b, because we have an interval where f of b is less than everything. We've got a local maximum here at c, but clearly they're not the greatest value of the function. We have an endpoint here and an endpoint here. So at the very least, if you have a function defined on a closed interval, you have to check the values at the endpoints. Because again, we're looking for an absolute maximum. I guess since we defined a local minimum and a maximum, we should have a definition for an absolute maximum. of f, there exists c such that f of c is greater than or equal to f of x, and f of c is an absolute maximum. So again, I'm just saying if everywhere we define the function, or everywhere we define the function, we look at the x's, and we find some value c for which f of c is always greater than or equal to every other f of x, and that's an absolute, f of c is an absolute maximum. So you can see why we have to check a, right? Clearly f of a is greater than everything else in this function. And, likewise, absolute minimum f of c will be less than or equal to f of x. You can fill in everything here, make this minimum. All right, so we have some formal definitions, local maximums, local minimums. We call these endpoint values. Clearly they're important. We're not quite done. Consider this function, f of x equals absolute value of x. Now, graph will help. Someone tell me, where is this function differentiable? Everywhere except null 0 here. Someone else want to tell me why it's not differentiable in 0? This would be a tricky question on an exam. Well, okay. So wave my hands. What did you want to answer?
The derivative does not exist. The derivative does not exist.
Well, that's a good answer, except it begs the question, what does it mean for the derivative not to exist? It's a good answer, though. So, as I said, the kind of wave my hands, not really answer it. I can say, well, it's got a sharp edge, sharp cusp here. It's like the tangent could kind of, if you want, like think of a fulcrum, you can kind of ride it around. It doesn't have a single value. The orthodox, you want to get your bachelor's degree, you would say, well, definition of the derivative is absolute value of, so it's the limit as h approaches 0 of x plus h, small h, problem with this limit is, as you come from this direction, you get -1. But as you come from this direction, you get 1. So it doesn't have a limit. So if you don't have a limit, you don't have a derivative. Okay. It's just a little side discussion. But we have a name for this when we're talking about maximums and minimums. This is called a critical point. Okay, I'm gonna define that. Critical point. I think the book uses the word critical value. Critical point is where either derivative is 0. That's good. That'll cover us when we have one of those local, one of these nice smooth local maximums. Or f of x does not exist. Okay, so we're ready to, we're almost ready to clean this all up. We've got some definitions. We've got a definition of local max and min. We have a definition of absolute maximum and absolute minimum. We know what a critical point is. So we just need a few more things to tie it all together. I guess I didn't say it. But this type of critical point where derivative doesn't exist, just like where derivative is 0, you can have a maximum right now. Clearly in this function, the minimum is 0, it occurs as 0, critical point. There's no derivative there, but all right. So the book sums this up kind of formally in 3 theorems. The first is going to need a little explanation. Otherwise, it should be obvious. This is the extreme value theorem. The hardest thing to remember here is probably the name. It says if a function is continuous on a closed interval, then there exists values c and d where f of c is an absolute maximum, and f of d is an absolute minimum. Okay, again, like many things in math, writing it out is more confusing than just kind of looking at it. You got some function, it's continuous. I can't take my pen off the board when I draw it. Somewhere on this function, however I draw it, there has to be a maximum, absolute maximum and an absolute minimum. Draw it this way. Okay, so here the minimum appears to be at the end point, and the maximum appears to be the local maximum, but it's also the absolute maximum. So that's number one. This second item is a little obscure. Oh, Fermat's theorem. Has anyone here, well, has anyone here heard of Fermat before? Just heard the name? Fermat's very famous mathematician. Has anyone heard of Fermat's last theorem? Well, there's a great stories. Fermat, he looked at this equation, x to the n plus y to the n plus c to the n, where n is, some number greater than 2, some integer greater than 2. Now, n were 1 or 2, finding x, y, and z that are integers is not hard, right? This looks a lot like the Pythagorean theorem. We have Pythagorean triples like 3 squared plus 4 squared equals 5 squared. But Fermat came up with this conjecture that if n is greater than 2, there are no integer solutions. And I think this was shortly before he died, too. He was writing a manuscript, and he writes in the border, he says, I have a very simple proof of this, but I don't have room to write it here. This is, I think, in the 1700s. And for decades and decades, mathematicians examined this problem. And they found proofs for like 3 and 4 and 5 and 7 and any number you can imagine. But they could not find a proof that this was generally true. And when I was in school, there was no proof. But I don't know, a decade and a half, maybe 2 decades ago, this math professor kind of came out of the woodwork. I wish I could remember names. You could just look up Fermat's last theorem, you'll get his name. He said, I have a proof. And here's my proof. It's like 100 pages. Now, to be clear, his proof was not a complete proof. He was using other things that had been proofs. And one of the things his proof was based on was some theorem, some obscure theorem that has to do with curves. Like if you have, curves between 2 points. I mean, imagine every possible curve between 2 points. And there's a theorem about them. And he uses this. This is like what math is often like at this very high level, where here you have something in a totally unrelated field. This is what we would call number theory, just integers. And now, like this analytical question about curves comes in. But he uses this. He's got 100 pages. There's only like a dozen people in the world could even understand this. But, this is a big deal. This has been a big issue in mathematics. a lot of good mathematics came out of attempting to solve it. So he has this proof, and a few months go by, and they say, wait a minute, you made a mistake here. This isn't right. So he goes, oh, see his whole plan was he went underground for about 10 years. He didn't want anybody knowing he was working on this because he figured maybe they'll start working on this idea I have, and they'll get it, and they'll get all the acclaim. But nope, cat's out of the bag. But he went back to work, and I think within a year he had fixed the problem. And so, this is no longer a conjecture, it's a Fermat's last theorem. Sorry, it has nothing to do with Fermat's theorem. Fermat's theorem says if a function f has a local maximum or minimum at C. Let's have something important. Continuous function f has a local minimum or maximum at C, then the derivative of f at C is 0. So it's kind of the flip side of what we've been talking about. I've been saying, well, if you have the derivative 0, then you have a local maximum. He's saying you have a local maximum or minimum, and it's continuous, then the derivative is 0 at that point. Okay, all this is, you can kind of file this somewhere. When you get to your PhD, you might have to look it up. But what you really want to know, this is the third item of the book, enumerates what's called closed interval method. For finding absolute maximums or minimums. Okay. So, given what we know, we just have to put it all together. There's nothing new here. So, let's say step A is find the critical values. Find any critical values. We're calling critical values, critical points are where the derivative is 0 or it doesn't exist. And actually what they want you to do is find the value of the function at those critical values. So if critical value is C, they want you to find f of C. The second step is find the values at the endpoints. Call this method is for a closed interval. And step C just says largest of these is the absolute maximum. And the smallest is the absolute minimum. Okay. So you take your function on an interval. Okay, you find the critical points. It's not defined here, it's not defined here, it's zero, the derivative is zero, here is zero, and you find the value at the endpoints. You compare them, and then whichever gives you the greatest value is the absolute maximum, and whichever gives you the smallest is the absolute minimum. All right. Let's do an example. I'll leave this here. So, So let's say my function is absolute value of x plus 1 plus 2, where x is greater than or equal to minus 3 and less than or equal to 3. Okay, so I guess it'd be helpful to know what the derivative of this is. We have to think a little, because when x is greater than -1, this is positive, and this is just like x plus 1. So for x greater than or equal to -1, this is 1. I guess I really shouldn't say equal to. It's not differentiable at -1. And for x less than -1, this now becomes negative x, so the derivative is -1. But the derivative at -1 does not exist. Okay, so that's our critical point, -1. And what's our value at -1? Well, it's 2. Okay, so that's one of the values we're going to compare. We need to look at the endpoints. -3 plus 1 is -2. Absolute value is 2. Plus 2 is 4. So f of -3 is, I should write that. F of -3 is 4. And we plug in 3, we get 4. 4 plus 2 is 6. Okay, so now we can see right away. F at -1 plus 2 is the absolute minimum. F of 3, which is 6, is the absolute maximum. So here we have a minimum at a critical point, and here we have a maximum at an endpoint. So, all right, well, why don't you try this example? What I want you to find is the, for f of x equals x cubed plus 3x minus 2. I want you to find the critical points. I guess I want this on an interval of minus 2 to I guess 4. Find the critical points, local max and min, and then the absolute max and min. I can go ahead and try that for a few minutes. So we're going to take a break. You can work on this on the break if you're not done with it. But I have a question here. Anybody have any thought on what happens if I take away this restriction with respect to the absolute max min? Have any idea about this? It's kind of a polynomial question from pre-calc. So if I get out here somewhere, what happens? this is odd. So if I come out here, I go like this, and in between here and here, no, it's gonna happen. Won't have an absolute maximum, right? I guess as large as possible or small. Okay, take a few minutes. I'm gonna take a few minutes. We'll go over this. Okay. How do we find the critical points here? Yonder. All right, so what's the derivative? All right. I'm going to let you answer in just a second, but I'm quite sure none of you suffers from that malady in which you take an exam and then you plug into the wall and then it erases everything. You don't need it anymore, right? I'm sorry. Go ahead. Okay, and that, we want to know where that's equal to, the derivative is horizontal 0.
You can't have negatives on imaginary. You can't have.
That be anybody have any idea what that means?
There's no critical points.
No critical points, no. This is easy. What do we need to look at? Well, we need to look at the endpoints. So, 2, -2 is -8, -6, -2. That's going to be the absolute minimum. It's 16. And f of 4, well, that's, everybody know what to do? No computer scientists in the class? Yeah. 64. Plus 12 minus 2, okay, so 76, 74, so that's the maximum. That one was too easy. Let's come won't be hard. It's easy. This one I guarantee will be more exciting. Much more exciting. You have a very low threshold of excitement. We missed very little. We're just trying another problem. Same idea. Find the absolute max. Have any critical points yet? Zero. And three. Get any others?
How about one? Have one.
Okay. Thank you. There wasn't, get that deal of confidence, not in the people who said anything, the rest of the silence. Let's see here. Derivative is what? Well, x cubed s 48x squared plus 36x. We want to set that equal to 0. Well, we should take out factors, right? So we've got each of these is like 12 and then an x, so x squared minus 4x plus 3. Oh no. Now we have to do factoring. But it's an easy factor. It's easy. 3 times 1 is 4, so -3, -1. So that's where the 1 and the 3 and the 0 come. Okay, good. Everybody should be able to do that pretty easily. So let's take a look at our values. F of 0 is, oh, that's nice. F of 1, I can still do that in my head. 18 minus 16 is 2, 3 is 5. 3, oh. Man. Well, that's 81 times 3, so 243. 27 times 16 is 54 times 8. 108 times 4. 132 plus 9 times 18. Well, I'm sorry, math. What am I doing? Yeah. 81 times 8. 729 times 2. Goodness. It's a big number. Is that right? So, alright, well, times 2. No. That's 9 times 18, 72. Oh, 81 times 2, 164. I don't have a calculator, but
Professor, 9 times 18 is 162.
isn't 18 9, 2 times 9 times 9, 81 times 2, 160? What are you saying it is?
162.
Oh, is that not what I wrote? Oh, I must have written, yeah, 4, okay, all right. So, 405 minus 432, 5 minus 32, negative 27? Okay. All right, so we're not done yet, though, are we? We're looking for the absolute. What else do we have to do here? that's 1, and that's -1. So I just add these numbers together. 34 by 37. And then I have that before. Aren't calculators nice? Nice calculator to help me. I can do it.
Maybe 32. 32.
32. Oh, thank you. Okay, so we look at these. This looks like the what? The absolute minimum. This looks like the absolute maximum. Okay, so a little elbow grease, a little assistance with your calculator. Now, those are straightforward. There's some gotchas. Things where I just let you go, you might, some of you would get them, maybe all of you would, but someone might stumble upon it. So, I don't know, this is weird. What do I do with this? What you do is you use the closed interval method. They're letting them in younger and younger now.
Are they jumping in the oh? I thought they're jumping in the wall.
How old
What's the youngest
There's nothing
you
inside.
know? I mean, nothing personal, but what's the youngest you know of a student, a freshman student at West End?
I've seen it.
17?
I'm still 17. What do you?
Into a school where the
Exactly.
the neighboring school had a habit of, neighboring school whose most famous, I don't know if she graduated, but I think she was Katharine Hepburn. They used to let in students, very few students were 15. It was a disaster. It's not mature enough. Okay. So math. Let's back to math. F of x equals 1 over x minus 1. Okay, so we want to know the absolute max and the absolute min. And I could draw this on the board and you'd go, of course. But I just want to, before we do that, let's go through this. So let's find any critical points. So first thing we want to do is find the derivative. What's the derivative of that? Minus 1, x minus 1 to the minus 2, which is minus 1 over minus 1 squared. We set that equal to 0, and what happens? Where is it? 0. Equation solving time. What x can I put in to get 0?
There is no x. Isn't there no x that you can
Double negative. Isn't there no? That would be, yes, there is a, no. I know what you, no, there's no x. There's no x. There's no critical points. Okay. I didn't give you an interval, did I? There's no endpoints. So, conclusion? No absolute min or max. That's what this is telling us. Now, if I draw the graph, it's like, oh, of course. What's the graph look like? Well, at 1, we have an asymptote, right? And it's gonna be a hyperbola. If you look at that graph, you go, well, of course there's no absolute max or min. There's not even a local max or a local min. So, you know, be aware, just because we learned how to find these things, that doesn't mean they always exist. Right? Now, the next one is cleverly designed to maybe, I don't know, maybe it won't fool anyone. Let's see. So here, f of x equals equal to 2x for x less than 1. And it's 1/2 x plus 3/2 for x greater than or equal to 1. Now, before we scratch our heads on this, I got to point out the obvious, which is this is a continuous function. This is a linear equation, it's continuous. This is a linear, it's continuous. So we only have to worry about what happens at 1. At 1, this is 2. At 1, this is 2. So it's continuous. Yes.
Does that just say x is greater than or equal to 1? Or
Yeah.
cool.
Sorry. I'm always fighting. My true handwriting is illegible, so I try and force myself to be more legible, but then sometimes I just get too excited. Yeah. Okay, so it's continuous. So, okay. Find any critical values. For points. F prime equals 0 or F prime does not exist. Any place here that F prime does not exist? Yes?
1.
Yeah. F prime of 1 does not exist. Well, maybe it's not that obvious. So we should, picture is worth more than 1,000 words in this case. Let's graph this. I hate to graph it at this point because it's going to give away the big secret, but we must. Okay, so 2x, that goes through 0. And 1, 2. So go like this, except that it's only defined. There it is. It's only defined up to 1. Okay, now 1/2 x plus 3/2, so that's going to have intercept at 3/2. It's going to go over 2, 1, 2, 1. But of course, it's only defined greater than. Okay. So there they are, as we saw, they match up. So that's my critical point. So, you know, f of 1 is 2. But it's not even a local minimum or a maximum, is it? So, absolute max and min, same for this, there is none. So this is another gotcha we have to think about. It would seem, we're going to find, you know, some more information, that if on one side of the critical point you're positive, you're negative, you're less than, and on the other side you're greater than, you don't have a minimum there. You don't have any kind of minimum. Okay. We're not quite done with the gotchas. One more here to look at. Shouldn't call them gotchas. They didn't get you. You just have to be careful. X equals x cubed. Okay. So, well, as far as critical points go, it's continuous and it's got a derivative everywhere. Right? So the derivative is 3x squared. You set that equal to 0, and you find x equals 0, f prime of 0 equals 0. Oh, okay. Well, that's local. Could be a local minimum or maximum. The only one could be the absolute, but turns out it's none of the above. And if you recall the graph of x cubed, it looks like this. And what's happening here? The derivative is positive, gets less and less and less and less, it becomes 0, and then it starts increasing again. So derivative positive, and then right here, derivative 0. Well, you can see that right here. We have squared. Like negative 1 would be 3, and positive 1 would be 3. It's always positive until it just briefly hits 0. And you do have a tangent here, it's the axis, but you have no local minimum and really no absolute minimum or maximum. So, it would seem we need a little more help here. We've got some of this, we can do some of these, but we need a little more equipment, machinery. Any questions up till now? Everyone's memorized this? up at the video. There'll be a video posted. People who are out sick. So what we come to now is called the second derivative test. Now, I want to let you in on a little something that's going to happen maybe Thursday, the latest, next Tuesday. We're gonna look at graphing things, looking at how the derivatives affect the shape, and that's really when we should be talking about this. But the book does things in its order, and I found that if I put things out of order in the book, it gets confusing for everybody, including me. So here we are at the second derivative test. It says, I'm just going to rewrite it. Well, a function has a second derivative at point C, and f prime of C equals 0, then the following will be true. If the second derivative at C is greater than 0, the function I don't like that, what I just wrote. Just copy it out of the book. Okay, well, it says here that then the function is increasing at C and f of, oh. Okay, got it. Yeah, the function, yeah, that's right. The function is increasing at C. Really meaning whichever way you go, it's increasing. And f of C is a local, let me draw that a little bigger. So it's saying, you know this is a local minimum or maximum because derivative is 0. But if you just look at the function, you might not know which way it's going. But if it has a second derivative, which is greater than 0, that means the derivative, as you move, the second derivative, well, the derivative is increasing. Right? The second derivative is positive, so the derivative is increasing. And that gives you a minimum. Likewise, if double prime of C is less than 0, the function is decreasing at C. And f of C is a local maximum. this situation, s prime c is equal to 0, double prime c is less than 0. Okay, just minor comment, is a local minimum, is a local maximum. That does not preclude it being the absolute. We're just saying could be maximum, absolute maximum, but it is a local. You might be confused by this. You might. I find myself confused by this. I'm looking at the derivative and the second derivative. And is it up? Is it down? Is it negative? Is it positive? And what you have to do is you have to think about this. You have to, you can't memorize it. You could. Hopefully you get it right. But it's much better to think about this. I've got a function. It's, we're going to learn this is concave up. Okay. Concave down. And it reaches some minimum. It's nice and smooth. It reaches some minimum where the derivative is 0. The tangent is horizontal. But how did it get there? It was a lesser number, a lesser slope. Slope is increasing. Here it's very negative and it's getting less negative. And here it's small, but it's greater. The second derivative is greater than 0. The rate of change of the derivative is in the positive direction. You have to kind of go through that motion in your head, get it clear, because then you never get confused on an exam or trying to figure something out. The same way, here I've got a tangent, and as I get close to this maximum, it's getting, the slope is getting less and less and less. It continues less and less and less. So the change in the derivative is to the negative. It's less than 0. And that's how you know that this is a maximum. That's kind of the pearl of wisdom here. You know, if you memorize the formula, you memorize these definitions, that may be good. You may have a, but if you can kind of get a feel for this, you're not going to get confused by it. Finally erase all this. So there's something missing here, of course. What if f prime of c is 0, and the second derivative, f double prime of c, is also equal to 0? Well, we don't know. We don't know if this is a minimum or a maximum or neither. Let's say the derivative is getting smaller and smaller and smaller, and it gets to 0, right? But at the same time, the rate at which it's getting smaller and smaller and smaller is going to 0. So you end up with f prime c equals 0, but you also end up with f double prime of c equals 0. Well, there's a couple things that could happen. One is that very slowly, as you go this way, f double prime could increase, and then f prime will increase. The rate at which it's going to 0 goes to 0, but then it comes back and then it goes up. So it could be a minimum. Or it could be at this point, the second derivative was decreasing and decreasing and decreasing and keeps decreasing. So the first derivative starts to get less and less. And we saw that. We saw that already. We saw f of x equals x cubed, f prime of x equals x squared, so that f prime of 0 equals 0. Or if we find the second derivative at 6x, the second derivative at 0 is 0. And then you get this kind of thing, except I have it backwards. It goes like this. So when you have this situation, you don't know, just looking at these numbers. This particular kind of point where the derivative changes direction. Here, where the second derivative changes direction. Here it's, down here it's negative, it's less than 0. But up here, it's greater than 0. And here it's equal to 0. This is called, I'm going to do this in, we're going to do this in another class. This is called a point of inflection. And keep it in here. Won't be late for your next class. I want you to think about this for a minute in your free time. I can have a curve that's kind of curving one way, and then it curves in another way. Right here, there's kind of a center down here. Here there's a center down here. And it's often hard to figure out exactly where that point is if you're just looking. It's a point of inflection. It's where something has changed. You're in a car and you're accelerating, and you take your foot off the gas, you're still accelerating, and then you're going at some speed, and then you're slowing down. All right, I'm going to put in homework assignments up in the next